kinds of bonds for chemical bonding. They're intermolecular and intramolecular. Now, intermolecular bonds are the bonds that will attach two different molecules together, and they're the repelling and the attracting forces that you've heard about forever. Now, intramolecular bonds are what the new stuff that we're talking about, and they exist in between individual atoms that make up a molecule. And they will affect the boiling points, melting points, and vapor pressures of the molecule. And so these would be examples that are in between stuff like NaCl and H2O.
Take two.
Hi. So one of the big things that most of you already know, since you already took honors chem or regular chem, you know a lot about chemical bonds already. So there's mainly 3 different types of chemical bonds. There might be more, I don't know. But we're going to go over 3 of them right now. So the first one is the ionic bond. Now, whenever you have 2 molecules with opposite charges, they'll be attracted to each other through electrostatic forces. A great example of that is sodium chloride. Sodium gives up an electron and becomes positive, while chloride takes that electron and becomes negative. And another type of chemical bond is covalent bonds. This one's far more common, actually. You deal with it a lot more anyway. So, for example, in water, in hydrogen gas and oxygen gas and all that stuff, lots of stuff, it's just sharing of electrons. So in hydrogen molecule, both hydrogen atoms will share an electron. That way they both get all the electrons they need. And then we have metallic bonds, which is pretty much, just imagine you have all the metal atoms surrounded by a sea of electrons, and then the electrons kind of just flow through that sea like they shell and stuff like that. But that's all pretty good. But we have demos to show how this works. So to begin, we have a light bulb, and what we're going to do with the light bulb, make sure you have your gloves on. Really important with these demos here is that you always have supervision. We have supervision right here with Gary. Gary's a snail, but he actually went to college for at least 2 months. Oh, and there's just Tegulans right there as well. He might have went to college. And so what we do is with this rate, actually let's do the dextrose first. So what we're going to do is we're going to take dextrose, which is a sugar, and this has lots of covalent bonds. We're going to add lots of it to this beaker here. Let's have the third one as well. Oh, we got some on the table. That's okay though. Anyways, mix that up, and we have a light bulb. What we do with this light bulb is it's plugged into the outlet over here, and it has these little 2 electrodes here. And essentially, if a charge can go between these 2 things, then then the light bulb will light up. But in the case of sugar, make sure it's really dissolved. We just take this and put it in, and nothing happens. Nothing happens there. So let's take that out, and let's wash that a little bit in there. Let that wash for a second. Now, if we take if we take the sodium chloride though, and we put that in there, and we stir that up, the sodium chloride actually. Well, both the sodium chloride and the dextrose both dissolve in the water, but when the sodium chloride dissolves in there, we get ions, and that allows for electricity to flow through. We get sodium ions and chlorine ions. Thank you. All right, yeah, that's pretty cool. That's nice. That's really nice. Like you put it in, it lights up. Wow. That's cool. Anyway. So now we have another demo. This one is, oh wait, no, actually we have one more. This one's really cool. So we just have water in here, and we have pickle juice in here. And the big thing about fruits, I like fruit, and what fruits do is they have lots of ions in the solutions that make the most. We have pickle slices here, and we have pickle juice in here. We pour the pickle juice in there. And you don't want to drink this. These pickles are actually really bad. I didn't try them, but they didn't turn out well. So we just do that. Plug the light bulb back in. Yeah, it's kind of glowing. A little bit. Oh, look at that. Yeah, it's glowing. That's nice. Let's turn the lights back on. Whoa. Alright. And now, here's the big show, like Super Bowl big, really big. What we're going going to do is we're going to take a pickle. Oh wait, let's explain this real quick. Sorry for the excitement. This is just a clock, but it's powered by oranges. I don't know how that works. So we're going to take a pickle, and let's get rid of that. We have a pickle. We have 2 electrodes plugged into it on either side, and this is plugged into an outlet. Well, it's not plugged in yet, but it will be plugged in a second. You don't do this at home. Don't do this.
Definitely, I recommend not doing this at home.
Don't do this.
He is under strict supervision.
I once stuck my finger into an outlet and it hurt a lot. My parents don't know about it. They also don't know about when I accidentally cut myself like with the knife. That was a different thing. Anyway, so we have this plugged in. Don't touch this, or you can die. Oh, nice.
Wow, look at that electricity.
Woo!
Nice. Pickle.
It smells.
Yowza.
Oh. And so that's that smells nice. So that's pickle. It's actually a burnt pickle now. We really don't want to eat it. And that's pretty much it. So what we just saw here is electricity was going through the pickle. Really concentrated pickle juice in there. Actual pickle juice, not distilled pickle juice. And electricity just flowed through. There we go.
As you know, bonding forms when the orbitals overlap. There are different types of orbitals, including S and P orbitals, which you have seen in your honors chemistry class. An important part to know about the bonds is that they form either sigma or pi bonds. In a sigma bond, as shown here, the electrons lie along the internuclear axis, which is, the internuclear axis is just the line between the 2 nucleuses. These kind of bonds occur in all covalent bonds because they draw the atoms together. This shows the overlap of p orbitals, but they can also be the overlap of 2 s orbitals or 1 p orbital and 1 hybrid sp orbital. In addition, there are pi bonds, which these are perpendicular to the internuclear axis, so the electrons are not concentrated in the middle. They only occur in multiple bonds, and they're weaker than sigma bonds because of the fact that they don't lie between the nucleuses. So in a single bond, you're only going to have one set of, in a single bond, you only have one set of sigma bonds. But in a double bond, you're going to have one bonding sigma bond, and then you're going to have a pi bond. Meanwhile, in a triple bond, you're going to have one sigma and 2 pi bonds. These bonds can be seen in resonance. A resonance structure consists of sigma bonds between the atoms, but then they also have they have a p orbital on each of the atoms, which forms pi bonds. So if the original structure would look something like this, however, like this or this, depending on how you want to picture it, this is more realistic. But when resonance happens, the bonds kind of, instead of having a double bond here and a single bond here, you kind of have a bond and a half between all of the atoms. And that makes the structure stronger than it would be. As you know, polarities when electrons are unevenly distributed around the nucleus. This results in a partial charge on molecules. This can be seen in the water molecule, where O has a partial minus charge, and the H's both have partial plus charges. On a diagram, this is shown by using a lowercase delta, as seen here. A dipole is simply another name for a polar molecule, and a dipole moment measures the polarity in debye's. The equation for a dipole moment is mu equals Q times R, in which mu is the dipole moment, Q is the charge of the atoms, and R is the distance between the atoms. This shows that as the charge and the distance between them changes, so does the polarity of the molecule. Polarity is used in deciding which substances dissolve in which. For example, a polar molecule dissolves a polar molecule, or a nonpolar molecule dissolves a nonpolar molecule. Meanwhile, a polar molecule is insoluble in a nonpolar molecule due to their attractions. Also, the polarity of a substance affects how it reacts to electricity and other properties of the solution.
Take 3.
The characteristics of polar and nonpolar molecules can be seen in this example. In this burette is cyclohexane, which has been dyed to be more visible. And since it is a nonpolar molecule, it will not react with the static electricity from this rod that has been created from the cloth. This can be seen here. As you can see, nothing happens. However, one moment. Make sure it's charged so that the lab will work. Water, which is a polar molecule, when it has the opportunity to react with the static electricity, it will bend as such. As seen here.
One. Or whatever this is.
Lewis symbols and Lewis structures should be reviewed at this point, but let's just go over it anyway. So Lewis symbols are just, it's essentially you just take an element's chemical symbol and you surround it with a number of dots in order to represent all of its valence electrons. For example, sulfur and oxygen have 6 valence electrons. They're in group 6, so we surround them with 6 electrons. The important thing to do when we're doing this is to remember Hund's rule, singly before doubly. So electrons, they surround the nucleus in pairs. So we'll have 1 electron before we have 2 electrons in each pair. And then with Lewis structures, it's pretty much the same thing. It's just Lewis symbols put into one diagram together. But when we have the sharing of electrons, when we have covalent bonds, we represent that with a line, which is just 2 electrons bond 2 electrons in one group together. Now, an application of this is the Vesper model, or the Vesper theory, which is pretty much just a way of predicting the shape of a molecule or the shape of an element or the shape of something like that through looking at where its electron domains or its electron pairs will end up. And a great way of representing this theory is with balloons, because balloons and electron domains behave in the same way here. If you have 2 electron domains or 2 pairs of electrons, they'll both repel each other. If you have them surrounding the same atom, they'll both try and go as far apart from one another as they can. The same thing happens with balloons when you tie them together. 2 balloons they'll start off as far apart as you can. If you add 3, they'll try and separate as much as they can. 4, 5, 6, so on and so forth. Now, so obviously if we take it down from 6 down to 5, the balloons will move a bit if we just let it do its thing. So let's see that. And this is what we saw there is it went from a group of 6 with 4 coming out either way and 2 coming out from the top and bottom to this where we have three balloons coming out like this with 120-degree angles between each, and then one coming out of the top and one coming out of the bottom. And if we pop another one like that, then we get a tetrahedral shape where we have 4 balloons coming out at equal angles from one another. And if we pop one last one, then we get a trigonal planar where we have 3 balloons in one plane, all with 120-degree angles between them.
Hi guys, today I'm going to talk about the 4 types of intramolecular forces. So the strongest force is ion-dipole. It exists between an ion and a dipole, pretty much. It's the strongest force. An example can be NaCl in water. Next is hydrogen bonding. It only exists between hydrogen, nitrogen, fluorine, or oxygen. It's the second strongest force. And you can see this pretty easily when it comes to water. You know, the forces hold up together pretty easily. They're pretty strong. Next is dipole-dipole forces, where a polar dipole is attracting to another dipole. The next is London dispersion forces. Now, these are the weakest force. these attractive forces exist between two different dipoles and two nonpolar molecules. So neither of the molecules are polar, which is why the forces are the weakest. And some examples are Cl2 and bromine. So here are some examples of types of bonding. Here's ion dipole, where it shows an ion, a positive ion, attracting to a dipole force. And you can see by the charges right here, this is the negative end, attracts to the positive. There's hydrogen bonding, which I talked about was the second strongest. Hydrogen, which only attracts to oxygen, nitrogen, or fluorine. Then there's dipole-dipole. This is the third strongest. So I guess you could say like third weakest. But the way it works is kind of like this. The dipoles attract to each other. The negative end here attracts to the positive end here. And what I'm trying to show with these dotted rings is that once they attract, the polar molecules kind of like squish together because of the attraction. Then there's London dispersion, which is like that, but it doesn't just occur in dipoles, it occurs in everything, which is why it's the weakest.
Chemical bonding test.
All right, let me look at this. All right. Great job. A+.
Wow.
There you
I
go.
want to celebrate this with you guys.
Alright, good work.
Bloopers.
Oh, you want to still see the pickup? Drive. If not, I just can't, because by the time I leave and stuff, driving is not open.
No. Oh god.
She didn't even know she was doing two-landers.